talk a little bit more about properties and changes in matter. And so as we do that, we had kind of introduced the idea of some physical and chemical properties yesterday: elements, compounds, mixtures, that kind of thing. Just want to go back and explain that after you kind of explored it. So matter is basically classified into two categories. You can have a mixture, or you can have a pure substance. And yesterday when we were going through the activity, we had figured out that a pure substance can be either an element or a compound. And that's just a broad umbrella term. Like a mammal can be all kinds of things, like a dog or a cat or a pig or a person. Pure substance is an umbrella term, and underneath that you can have a compound or element. It's just a way of classifying, and we're talking about classification, so it makes sense. A mixture, they're not in fixed ratios, and also they're not chemically bonded together. So when we start talking about a mixture, whether it be sand, like we just discussed, or it could be something like salt water, the salt and the water they're not chemically bonded. There's certainly some interactions that are going on there that are really interesting that we'll get into later in the semester, but they're not in a chemical bond. And they can be separated by physical means. And when we talk about separating by physical means, later on in the semester we'll be talking about solutions, so we'll do that a lot. But for right now, what we're referring to is, we could do something like we could separate them by filtering them through a funnel. I forgot the filtering part. And so we could take some filter paper and put it in a funnel and pour it, and it would separate, for example, if it was sand and water together, or something like our dirty dishwater. That's really gross, but it's in there. So we could do that. We could filter it. If we had some kind of precipitate, and I actually got some stuff to show you on precipitate today, so if you don't know what that is, some of my people in first period have heard that word before. Have you heard the word precipitate before? A couple of you? Okay, cool. So I'll show you that. We could also do something like we could distill it. So distilling something, has anybody ever watched like the moonshine shows on the Discovery Channel? You watch that? Or, okay, you live in Bartow County, let's just be honest with each other. Like, a moonshine still is a thing, and I think you've all heard of it before. Have you heard of the moonshine still? Yeah. So, do you know the word still is coming from the word distill, and that just means to boil. So, if you, make some moonshine, what you do is you take some corn and you make mash, and you, mash it up, and you let it ferment, which is, where you take this corn, the carbohydrates in it, and you turn it to ethanol, to alcohol. Anyway, when you go to separate out the alcohol, so you go to separate out the moonshine, alcohol boils at a much lower temperature than water. And so if you've ever watched those movies, they have a fire going, and then they have their whiskey, their mash sitting on the fire, and then they have all these pipes, and they're pulling the alcohol off by boiling it. And it boils at a lower temperature than the water, so the water stays behind in that big barrel, and then the alcohol gets boiled off, and then they can collect it. And so that's distillation. And so alcohol is a solution. Not to your problems, but just in chemistry. I did. I only have 3 jokes. Give me a break. But anyway, it can be separated by physical means. Not by boiling, but you can separate salt and water by letting the water evaporate. You're not having to separate it by actually doing a chemical reaction. So that goes along. And you could certainly boil the water to make it go faster, but it will evaporate on its own over time, a little slower. So there's that, and so there are 2 kinds of mixtures. There's homogeneous or homogeneous, whichever you like, and heterogeneous. And so we talked about homogeneous mixtures there. They look, it's to the eye. Does it look uniform throughout? Or with heterogeneous, is it, can you see the various parts? So it looks the same. Everything, is mixed together. You can't see the various parts with homogeneous. So I have some examples here. We have water, and that's probably, it could be salt water. I don't know. I can't see the salt, but it could be tap water. Tap water has ions in it. Certainly going to have some chlorine in it from disinfection. Other minerals for taste. An alloy here, this steel, stainless steel. Steel can have carbon in it. It can have nickel in it. And I can't see those different elements in that steel. So, also the air. I just need to tell you today, because it's important to me, the air is 78% nitrogen and it's actually 21% oxygen. So people commonly have this misconception that air is oxygen, and so we can just breathe in, we're fine. And that's true, certainly we can breathe and be fine, but it's only 20% or 1/5 about oxygen, and the rest is nitrogen, which is not, definitely not anywhere close to 100%. Later on today, I forgot, I don't think I started my data thing. So let me just start my little data probe for you.
Is that spelled natural or is it the part of
This is, Mr. Harden actually put some crayons on it, and that's what you're smelling. Okay. Isn't that fun? I'm going to start the data collection for you guys so you can see it. So there it goes. It's cooking. All right, so anyway, I know y'all wanted to see the data. Yes, sir.
What's the other 1%?
The other 1% of air is 0.9% argon, and then you have trace amounts of water vapor, carbon dioxide, things like that. But the most of the other 1% is argon. So those are solutions. When we think about solutions, typically you're going to think of a liquid with another liquid or a salt mixed in, but it actually doesn't have to be a liquid. So when we think about solutions, it can be something like 2 gases or several gases with air. So it could be gases, it could be in a liquid phase, and it could be solid. So, and the alloy is a combination, like I said, of metals. On your test, when you're taking your test, okay, one of the questions is asking you about alloys. You already know the first 100 elements. And so when you're asked about alloys, you are given some choices. And so let's say your choices were stainless steel, and then maybe like bronze, and then maybe something like pewter. Are those things that you've heard of on the periodic table before? No, so those are all alloys. But then if you see, if it's asking you to identify the element in that series, and then you see a metal like cobalt or zinc, then of course that's going to be the element. And the other things that you've never heard of when you study for your elements quizzes, then that would be, those would be the alloys. And so learning our elements, you guys did really great with that. But learning those elements is so important because, it really opens up a lot of ability to kind of differentiate between what you're talking about. And like I told you, it's like learning your letters before you learn how to spell. All right, so heterogeneous looks different. You can actually see the various parts. This is real straightforward. So you have nuts and some trail mix. Most rocks are heterogeneous mixtures. And then if we have a volcanic eruption, you're going to have various parts of ash and rock and dust and gases all mixed together. And you can kind of see that. So most food is heterogeneous. Soil, smoke in the air, dirty water, and rocks. So we don't deal with a whole lot of heterogeneous mixtures in here. Most of the stuff we'll be using are solutions, so that would make them a homogeneous mixture. So we'll be making solutions and working with those a lot. All right, so pure substances, like we talked about yesterday, these are either elements or compounds. And so if I have hydrogen or oxygen, that's an element, or excuse me, but here, if you look here, I see this little 2, and so at that point when they're bonded, it's then a compound. Hydrogen and oxygen and several other elements can't exist by themselves. They can't just be an H or just be an O. They have to be bonded, so we'll certainly get into that later. But anyway, elements are alone. Anytime you see these little numbers down here, they're in bonds. And so the ones on the test are really straightforward. It just has the word, and so you won't have to know that H2 is in a compound, but H is not, because that's something we haven't talked about too much yet. So anyway, elements, only one type of atom. So here I have silver, here I have gold. I think that's really pretty. And these are going to be things from the periodic table. So if it's from the periodic table, then it's an element. It's pretty simple, especially when the periodic table is called the periodic table of elements. That is its full name. I see it on the wall. So anyway, here I have some mercury, some little carbon there, and some copper. Here I have some titanium, and this is what sulfur looks like. And this is gold. So there you go. And then we have compounds, like I said, 2 or more elements chemically bonded together. And the big thing here is they have to be, to separate them, They can only be separated chemically. So you're not going to be able to, you're not going to be able to distill this or filter it. So you're going to have some kind of reaction to actually separate it. So, the things we had talked about, filters and, melting and stuff, boiling, that kind of stuff, it's not going to work. Not going to separate. Is my water boiling yet?
Yeah.
Are both of them boiling or is that one? Oh boy! Okay, so time out. I need you to do me just like a real quick little favor. On your paper, I just need you to draw me a little beaker. And I need you to draw me 2 little bubbles. See the bubbles that are boiling? I need you to draw me 2 little bubbles, and I want you to tell me what's in those little bubbles. You can do it on the side of your PowerPoint. Do you think they're both 100?
Yes. It should be.
Should be. So just draw me a little beaker, and I need you to put 2 little bubbles and tell me what's in the bubbles. So if you think water's in the bubbles, put H2O. If you think oxygen in the bubble, put O2. Whatever you think. Alright, so come and check out the graph. If you want to, I'll hold it up for you. Uh-oh, I lost my temperature. So they are at the same temperature. You see that? You can get up and come see. And I can go back to the screen where it has the numbers, but you can see that at the same temperature. If I let these boil forever, they will never be above 100 degrees. And I'll let it boil because I don't think you believe me. We'll talk about why that is later because it's really interesting. But they'll just stay flat for the rest of class. It won't go up anymore. Can y'all see that it's safe? Okay, cool. I'm going to set that back down. And we'll just let our little water boil. So let me see what's in your little beaker in your bubbles. I'm looking for your little bubbles. Have you labeled what's inside of your bubbles? We are quite a house divided, I will tell you that. What you got in there? Oxygen. See some water, see the oxygen. Oxygen, oxygen and hydrogen.
What'd you put?
Water. Oxygen. Water. Maybe we need to take a vote. I don't know who's going to win. American Idol, thank you. Oxygen. Water. And what did you write down? Okay, so let's just talk about this for a second. Let's just talk this out. Are we talking about, you ready? Let me help you reason through this. Now, is this water boiling? Is this a physical change or chemical change? So let me ask you a question. In a physical change, do I make a new substance?
No.
So, could those bubbles actually be oxygen?
No.
You know why? Because I don't make any new substances when I change the states of matter on this. When I boil this water, those bubbles are water vapor. You know how I know they're water vapor? Do you think my hand's moist right now?
Yep.
Sure is. That's the thing, y'all. This is what clouds are made of. This is how that works. Yeah. And so these little bubbles here they're just water in the gas phase. And so, I mean, you guys know you make spaghetti at your house, right? And if you touch the underneath of your cabinet, your microwave, whatever's above your stove, it'll be wet, right, after you boil water. That's just because the water just condenses back on the top of your cabinet. This is just water vapor. And I know that because, well, I know that, but this is a physical change. I can't make hydrogen and oxygen. The only way you can do that is you have to put electricity through water. It's called electrolysis. We talk about that in AP chemistry. But this is a physical change, and those bubbles are water. And so really this week we learned how to graph a line. What happens when you boil water, right? And when we talk about a substance, the properties of it stay the same. I mean, some just real basic stuff, but it's good. I mean, this is making you like a functioning human being. So I'll see if it's still at 100, then I'll go back. Anyway, you can do one of two things with of substance. You can either make it hotter or you can change the phase. Both can't happen at the same time. So guess what's happening right now? I'm changing the phase, so it won't get any hotter. I can make steam hotter, but I can't make liquid water hotter. But I'll let it keep boiling because I think this is just really cool. Yes, sir.
Okay, so does it always boil at the same rate if it's always 100 degrees Celsius?
So if I had a whole bunch more water in here, then it surely would take longer to heat up, right? But it would always boil at 100. It may take longer to get to 100 because you know that you go bake macaroni, you put a little bit of water in the pan versus a lot. It's surely going to take longer with the more water. And that's, we're actually going to do the math that supports that later on in the semester. So, anybody else? Now look. Deep thought from Miss Brand. All right, come on back with me here. So water is a compound, certainly, and we can only separate water because it's a compound. We can only do that chemically. So we can separate water. We can put something like sodium metal in water, and it will split it into some hydroxide and hydrogen gas for you. We can run electricity through water, and it will split it into hydrogen and oxygen. But that physical means of boiling it, that will not make a new substance. And so we just kind of talked about that. They have fixed ratios. Every sample of that water over there, if you took samples, they would all have 2 hydrogens to 1 oxygen. So water, carbon dioxide, sodium chloride, those are all compounds. So there's water and salt. When we talk about properties of matter, once you know what kind of matter you're discussing, whether it be a compound or an element or some kind of mixture, we're going to have physical properties and chemical properties. And so when we look at this, physical properties, they don't lead to a change in the identity of a substance. And so the big one that we've been discussing that we have done in depth is density, right? And so if I test the density of water or aluminum or whatever, it's not gonna change. So something like density is an intensive property. So it's not going to change even if I change the amount, because like we had talked about yesterday, if I increase the volume of aluminum, I'm also going to be increasing the mass of the aluminum at the same time. So that density is going to stay the same. The color of aluminum is not going to change. Certainly the shape and all this, I could cut it into different pieces. That would change, but I'm not going to make a new substance, right? Boiling point, melting point. These are other ones that are physical properties. The reason boiling point is a physical property is because when I boil something, I don't make a new substance. And we're going to talk about these changes in states. That's this whole little unit later. All right, so physical properties, I don't make a new substance. And things like density don't change. Boiling point, melting point don't change. I can certainly change it by, cutting it, pouring it into a smaller beaker. That would change the shape and the size, but I'm not going to change the actual substance. So physical changes, like I said, change in the phase or state of matter, change in the shape or color. I don't know that I fully agree with my color there. I'm going to renege on that. Okay, so chemical properties. These are properties that relate to a substance's ability to change identity or when it changes identity. So if something is flammable, for example, if I'm talking about wood or if I'm talking about gasoline, when I burn wood or I burn gasoline, those properties related to that, when that occurs, that makes a new substance. When I burn something, I make carbon dioxide and water vapor. When I burn gasoline, that's the same products. Whether it reacts with something else. And so this is really funny. I took this little paper clip and I put it to show displacement, I put it in the graduated cylinder, and I showed a couple people how to do volume by displacement. And I left it in here. We had our little snow day, and it actually oxidized. It has, you see the rust in there, right? So it rusted. And so its volume, that was a physical property, and its chemical property is that it oxidizes in oxygen and water. So I made a new substance. So iron oxide is a new substance, FeO, right? So they're bonded together, stuck together. Yes.
So is color like both?
No. Color change. When something changes color, it is a chemical change. But the color of something is a physical property. Do you see the difference?
Yes.
Okay. So anyway, what it reacts with, if it's flammable or not, those are chemical properties. And those can lead to chemical changes. Here's some chemical changes. Here I have a couple pictures of a building and the Statue of Liberty. These are both made out of copper. And the copper can oxidize and it can make this nice patina color. Does anybody have copper like overhangs on their windows at their house? Have you ever seen those? They're on kind of fancier buildings. No? So anyway, the Statue of Liberty, when France gave it to the United States, I think it was on our 100th anniversary for our country. I'm pretty sure that was it. It was? Okay, cool. I'm always, my history trivia, like I have so many random facts in my brain from teaching AP Environmental. It's just like, but anyway, when they gave it to us for our 100th birthday, it was copper. It was the color of copper. It was that orangey, browny, bronzy copper color. And now it's green. And so that copper is oxidized. Here we have some sugar getting burnt, and so these things we're getting gases involved, we're changing the color, we're changing the properties of these things, and so those are chemical changes, and so that's really going to be the fun part of chemistry. Here we have some silver kind of oxidizing, and then we have the combustion of wood, and that's actually rapid oxidation too, combustion is, but burning something certainly does. If we see something that involves a color change, the formation of a gas. So if you're looking at a reaction, which on Monday we have some physical and chemical changes that you're going to go and rotate through, and you're going to have to provide evidence for if they're physical or chemical change. Well, here's the evidence for chemical changes. And so when you're going to be looking for this, if you see, well, how can I tell if a gas is made? Well, it'll have some bubbles, okay? And I know that sounds really fancy, but that's it. You can get a precipitate, and this is a precipitate, and I have this, I'm going to make it for you. Burning something, anytime you have a change in temperature, sometimes you'll mix two things together and it'll feel cooler. Sometimes two things can be hotter, like with combustion, right? So anyway, let me do this little precipitate for you because people don't know what a precipitate is, and so this is actually a nice little double replacement reaction, which you don't know what I'm talking about yet. Can you all see this? I like this. So how about I stand, how's this right here? Can everybody see right here? So I just have some lead iodide and potassium chloride, and I'm going to make some nice yellow. Is that pretty? So I'm making lead chloride. And can you see how that looks cool? Do you see how that's a nice solid color? It's not see-through anymore. That's a precipitate. Precipitate is a solid form in this little double replacement reaction. You don't know what I'm talking about yet, but you will. So, and as we let that sit there, it's actually, since it's a solid, it's gonna settle to the bottom. And so at the end of class, we'll have this nice little yellow layer of solid, and then you'll have that solution, that homogeneous mixture on top of it. So there you go. That's what a precipitate is. So when you form a precipitate, then you can tell you have a chemical reaction. Alrighty, so there's that. And moving on. Like I said, when we do this lab on Monday and you have to provide the evidence for each of we're going to rotate through stations. Each of them have the evidence whether it's a physical or chemical change. These are the pieces of evidence you're looking for a chemical change. So density is a physical property. It is constant, just like boiling point, melting point, all those are for a substance. And it's mass divided by volume, or when we looked at the actual pieces, the little particulates, and we drew the little graphs, it was constant. We counted the little particles in it, and then it was how much mass or matter was in a volume, okay?
Excuse me, Ms. Freeman, I need Christian Welch to check out.
All right.
Thank you.
And so density is mass divided by volume, and so here are my units. It's grams per milliliter or grams per centimeter cubed. I will caution you when you go to take your test next week, it is usually these two things, but it can be any unit. It can be any unit of mass divided by any unit of volume. So, you know, it could be kilograms divided by liters. It doesn't have to be just grams, right? But this is what conventionally we're going to measure it in. It would just have to be a unit of mass divided by a unit of volume. And so when we're calculating volume, it's length times width times height, 4 cubed. On your test, how do we calculate area?
40 times width.
Yeah, so, and what would be, and so this is going to be centimeters cubed for volume. What would be the units for area?
Squared.
Yeah. Do you feel comfortable with that? You sure? Okay, good. And then the last one, we can put into a graduated cylinder or some other volumetric device that has little marks on it. We can measure the volume before and after and subtract, and you guys did that final last initial. Here with this graduated cylinder, it's to the ones place. So when we record with correct significant figures, what decimal place do we need to go to? The tens place. So this is actually 7 point, and I'll get a different color. This is actually going to be 7.0, and this would be 9.0. Don't forget that extra decimal place, and don't forget to put your units. All right, all the time, every day. So there's that. How do you feel? Yes, sir.
What if it doesn't give you a unit? Like that doesn't give you a unit?
So a graduated cylinder is always going to tell you on the side what it'll say milliliters. So there's always some little place on a volumetric device sold to scientific people or classrooms. It'll always say on there, but conventionally it's going to be milliliters. So there's that. And so why don't we take a second and go ahead and get out your paper that you picked up, or not picked up, the one that you made the list, and we're going to watch the movie and you're going to be able to add to it, okay?